Walaikum assalam. So let's continue. This is one very simple example. I think it shouldn't be difficult to you. Okay, suppose a permanent space station is built on Mars and the station communicates regularly with Earth. Distance between Earth and Mars is approximately 100 million kilometers. 100 million kilometers. Okay. Calculate the delay between transmission and reception of a signal sent from Mars and received on Earth. Okay, time delay. In order, to in order to calculate the time, if we know distance and velocity, we just take the ratio between distance and velocity. Okay, distance is 100 million kilometers. It means, okay, 100 million is 10 to 6 multiplied kilometers. If we switch kilometers into meters, we add 10 to 3 meters. And what is the VP? VP in our case, we we know that the medium, in our case, medium between Mars and Earth is free space. That's why VP in our case will be just c, or speed of light, and c is in our case c is 3 10 to 8 meters per second. So if we divide this, okay, here we have 10 to the 9. Here we have 10 to 8. If we simplify this with this, remains only 10. 1000 divided by 3. So 1000 divided by 3 is 333. 333 seconds. Well, as you can see, this is a delay of over 5.5 minutes, or 5.5 minutes. Or in other words, if we say if we need a response, here we calculated the delay between transmission and reception of a signal, and if we need a response from the let's say from the Earth, it will be more than the twice of this time, or response time will be something about 11 minutes. And well, this also means that timing of any radio controlled equipment must take into account this delay. Okay, this was very simple example for the beginning. Now so far we have found a solution. We have found solution and discussed electric field intensity. Okay, here we have found a solution in terms of electric field intensity and discussed only electric field intensity. Now, okay, according to the Maxwell's equations, that the magnetic field intensity H exists whenever electric field intensity exists. Therefore, for a complete discussion of electromagnetic wave, we must discuss the magnetic field as well. Okay, let's take Maxwell's first equation in time harmonic form. It was rotor of E was equal. Okay, Maxwell's equation in time harmonic form was Maxwell's first equation. Okay, it was, if I'm not mistaken, it was somewhere here. Okay, this one in time harmonic form. Let me put it here. So rotor of E equals minus j omega mu h, and rotor of E equals to what? Equals we have done this cross product several times. That's why I will not repeat every procedure. I just write the rotor of electric field intensity is equal D will be dEz over dy minus dEy over dz plus y dex x over dz minus dEz over dx dEz over dx plus z. So dEy, yep, dEy over dx minus dex over dy. So equals. So what is this expression? This expression is minus j omega mu and sum of three components, x hx plus y hy plus z hz. That's why this will be equal, everything will be equal to minus j omega mu, so x hx plus y hy plus z hz. Okay, if we look to our final expression, now if we remember first, if we remember, we are working with one-dimensional wave equation in free space. It means that our electric field was one-dimensional, was in x direction, ex z. Yep, our electric field intensity was in x direction, and other components were 0. EY was 0, EZ was also 0. And if we know that EZ, EY is equal 0, EZ is equal 0, this term will be 0, this term will also be 0. It means we will not have component, okay, component along x is 0, and if we look to the right hand side of the equation, okay, we are working with this equation. If we look to the right hand side of this equation, okay, from the left hand side we found that there is no component along x from the left hand side. It means from the right hand side also there shouldn't be component along x. It means, okay, this component is 0. This means this component will be 0. Okay, on the left hand side, let's switch to the second component. In the second component, okay, EX again 0. So sorry, EX is not 0. Sorry. So we have component along x which varies with respect to z, or which varies along z. That's why this component is not 0. What about this component? This component is 0 because Ez is 0. So because of Ez is 0, this component is 0, and we do have y component. So we do have y component from the right hand side also. What about component along z? So EY is 0, simple. Okay. What about EX? EX is not 0, but EX is not 0, but EX depend on Z. If EX depends on Z and EX is independent of Y, this derivative will be also 0. So we will not have Z component. Okay, Z component as well simplifies. So okay, let me continue here in order to conclude. Okay, that was awful. Wait. Okay, I think it is visible. Well, from all of these, what we have that y dx over dz is equal, from the right hand side, minus y j omega mu h y. Okay, we may simplify unit vector y as well. So we have dx over dz will be equal to minus j omega mu hy minus j omega mu hy. Or so or if we write this, so okay, we have this. Or if we write this for the forward propagating wave for hy, so hy, sorry, hy plus forward propagating wave along z will be equal to what? Will be equal to minus 1 over j omega mu multiplied dEx over dz. Or if we multiply here j by j, we have j over minus 1 and minus simplifies, so we have j over omega mu multiplied dEx over dz. Okay, from our previous lesson, we know that, well, here it is plus, here it is also plus, because we are dealing with a forward propagating wave. Okay, if we remember, forward propagating wave, the ex plus in terms of z was equal to E0, so E0 plus e to the power of minus j kz, and we take it and replace it here and calculate the derivative. So what will be the derivative of dEx with respect to z? So dz, okay, Ex is E0, E0 plus e to the power of minus j kz. It will be minus jk minus jk E0 plus e to the power of minus j kz. Or this expression is again Ex plus against z And what we have? We have minus j k ex plus z. Okay, please don't be confused. Here k was a wave number, was a constant of wave. uh, K is not a complex number. Don't confuse. Don't be confused. So we compute the derivative of ex with respect to z. These two are equal. Okay. And the derivative of ex with respect to z is equal to minus jk ex z. And if we put it here, we replace the derivative. So what we have is hy plus, okay, z is always z, is equal to j over omega mu. Okay, sorry, let me a little bit scale down a little bit. Now it's good, it's better. Hy z, okay, plus is equal to j over omega mu multiplied, the derivative is equal to this, minus j k ex, so ex plus, okay, j multiplied by j is minus 1. Minus 1 by minus is plus. And what we have? K over omega m k over omega mu ex plus. And the final expression for magnetic field intensity H y is equal k over omega mu ex plus, and the unit of measurement was ampere per meter. Okay, as we mentioned in the previous lesson, the reference field is electric field, or the reference field is electric field intensity E. That's why we define the ratio between electric field intensity and magnetic field intensity, or in other words, we define Ex Z over, so HYZ, and we define it as a Greek letter eta, and is equal EXZ over EXZ simplifies, omega mu over K will be equal to omega mu over K Okay, if k we substitute with omega square root of mu epsilon, we get square root of mu over epsilon. Okay, what is the unit of measurement of eta? The unit of measurement of eta is ohm. Ohm, because the unit of measurement of electric field intensity is volt per meter. Unit of measurement of the magnetic field intensity is ampere per meter. And so if we take the ratio will be volt per meter, and volt per meter is ohm. The unit of measurement of eta is ohm. Okay. Okay, and eta is called as an impedance, as an impedance because the unit of measurement we are getting is exactly the same with the unit of measurement of impedance, and eta called as intrinsic impedance or wave impedance. Okay. Intrinsic, so intrinsic impedance or wave impedance. Okay. And so we may, for example, we may compute the intrinsic impedance of free space. Intrinsic impedance of free space. Well, we may compute this as, we may denote by eta 0, which is mu 0 over epsilon 0, and which is equal to, so mu 0 is equal to 4 pi, 4 multiplied by pi multiplied by 10 to minus 7, and epsilon 0 is equal to 8.854 10 to minus 12. Okay, if we compute this. 4 pi 4 multiplied by pi is equal to 12.56. If we divide it by 8.854 is equal 1.42, 10 to minus 5. Or, okay, we 10 to 5. Okay, we multiply this 10 to 5, and the square root of this will be approximately 376.73 ohm. Okay, the intrinsic impedance of free space is 376.73 ohm, and for application purposes we may say that intrinsic impedance of free space is, we may say, is equal to about 377. Okay, and now the equation for magnetic field, or equation for Hy plus, can be written as 1 over eta multiplied Ex plus. Well, everything depends on z. Sorry, here Hy z is equal 1 over eta multiplied Ex z plus. Okay, several words. We may notice that both H and E, in our case, Hy plus Ex plus, both H and E propagate in the same direction and are orthogonal to each other and to the direction of propagation also. So these two propagates in the same direction and orthogonal and are orthogonal to each other and to the direction of propagation. Okay, this property makes E and H, or electric field intensity and magnetic field intensity, transverse electromagnetic waves. Okay, and relationship the relationship between E and H can be seen, okay, in this picture. Yes. Here you may see the relation between electric and magnetic field intensities in a plane wave. So this is the electric field intensity uh, which has a component along x and varies along z or propagates along z. And this is the magnetic field intensity. I draw with red. These are the magnetic field intensities. The magnetic field intensities have components along y, and they also propagate along z. Okay, in red we have magnetic field intensities. In black we have electric field intensities. So let's see one example. Okay.